Good morning, student. Today's class will discuss about the crystal lattice. So, what is actually the meaning of crystal lattice and so on? We'll discuss in today's class. So, class, we just start with this crystal lattice. So, in the previous class, we just discussed about the introduction of the. We started with this, right? The single crystal, what is single crystal and polycrystalline solids. So we just have a brief overview of what is the meaning of single crystal. So atoms which are completely repeating itself are the imaginary points, which is repeating itself in a given space, right, to the entire extent of the material. So we just say that if this is the case, it is known as single crystal. And what is the meaning of polycrystalline solid or polycrystalline material? So what is the basic difference between the polycrystalline solid? Uh, so it is actually compromised of many small crystals, and these many small crystals are nothing but we'll call that as grains. So grains are nothing but small crystals, uh, and which have a different orientation, and which we say that if this is the case, then the given material is said to be polycrystalline material. So this is a semantical view which we have already seen in our last class, right? So you can just see this. This is the overview of the polycrystalline solid, how it is looking like. Uh, so you just it is a model of the nanocrystalline solid, right, of a particular material. So what is actually the meaning of crystallinity? So here, see, this particular concept is actually uh, three-dimensional, right? So we need to understand it two-dimensionally. So that is the reason that we need to consider some important parameters, in which the first one is the lattice points. So see, we want to study element, right? And that element is actually a three-dimensional element. So our naked eye cannot see that three-dimensional element. So we need to imagine the three-dimensional element, right, in two dimensions. So in order to do so, we need to just consider some important points. And what is that important points? I will let you know, right? So here you can just see this. Uh, they see what is actually the meaning of crystallinity. It is a periodic array. What is periodic array? It means if the points or the atoms or the molecules or the ions are arranged at an equal distance, right? So we just say that that is called the crystallinity, right? Now, so in this particular aspect, so what is the definition of crystal structure? So the manner in which the atoms and ions or molecules are arranged with equal spaces. So we say that it is called crystal structure. You can just see this semantical view of the structure of the crystal. So here, so in order to understand this three-dimensional aspect, we need to consider some important points here. So here we are just considering first of all the space lattice. See, what is the meaning of space lattice? How you define space lattice? So space lattice can be defined as with respect to three dimension, right? So with respect to three dimension, a periodic array of points, and each point will have identical surroundings. Now, what is this meaning of identical surroundings? We'll just see this, right? So you can just see the schematic diagram in which it is, see, the imaginary points which are arranged in sequential order. You can see the imaginary. This is these dark spheres, whatever you are seeing here, they are imaginary points, and they are at equidistance, right? At equal distance. So what we are considering is that, let us consider an aspect of since aspect of two dimension. So since this is the plane, whatever you are seeing in the screen is a two dimension. So the distance between the two points here, respective neighboring points, is nothing but A. And here the distance between these 2 points is P. So how we can write it mathematically? So that is given by the particular vector, which is given by, see, you can just see U R U V UA plus VB, which repeat a point along a two-dimensional plane. And what is U and V? U and V are some integers, and that why we are taking only integers here? See, we are taking integers that this point may be positive, uh, or may be negative. So that is the reason that the position vector is given by UV is equal to UA plus VB. See here. So first of all, you can there will be some what you can say doubts regarding what actually we are trying to learn. So this is what we can say that we want to study the crystal structure, right? First of all, so in order to use the solids for different application purposes, so we need to understand the concept of the detailed concept of the crystal structures, right? So if you understand that structure of the crystal, then you can easily know that how these crystals can be used for various applications. So in order to um, know these applications, we need to consider some important points, right? Two dimensionally. So this aspect is completely three dimension, but what we are saying that this is this is two dimension. So here the lattice points, first of all we need to understand in a two dimension space, we need to understand that each lattice points has an identical environment. You can just see this is an imaginary points. You see why we are considering this imaginary points? See, we don't know, we cannot see the from our naked eye we cannot see exactly what is actually the atom is, how the atoms are arranged. So we are just imagining the maybe the atoms will be arranged in a particular sequential order. So each lattice point, so we said that the imaginary points are nothing but, we say that is called lattice points in physics language. So each lattice point has an identical environment, means the dots, whatever you are seeing, the dots are nothing but we are imagining that that are the maybe the atoms may be arranged in this particular format. And if this is the case, so we say that that are imaginary points, and each point is having the same environment with respect to the other. You can just see a semantical view of this different lattices. See, there will be different lattices I have shown in the figure. So we need to know this. See, different lattices, how these lattices are arranged. So depending upon their arrangement, so they are considered to be oblique lattice, square lattice, rectangular lattice, hexagonal, rhombic, and so on. Now, so I will just make you understand this very clearly within video also. So first of all, we just what we'll do is that we'll just start with our uh, imagination of the lattices. So here, you see, the lattice is nothing but is a regular infinite arrangement of the points, right? We are just going for now. We're just starting with the imagining some points here. So lattice is this regular infinite arrangement of points in which every point is having same environment with respect to the other. So if this is the case, see, in two dimension and three dimension, what will be the case for two dimension arrangement of the point and three dimensions? Here you can see this. If this is the case, we just say that is called two dimension arrangement, and this two dimension arrangement can also be semantically viewed, right, in three dimension also. So for in order to have very clear idea about the lattice points, so we just have a definite what you can say picture to understand this lattice points. So you can just see that lattice is nothing but infinite array of points, and each point is having the same environment. So the lattice points, depending upon the dimensions, so they have been classified into three different categories. If the first case, you can see this is one dimension, and we say that that is called linear lattice. You can just see that these points are arranged at equal distances, and these equal distances, arrangement of equal distances in a particular dimension. So we just say that that is called linear lattice. So what is the meaning of linear lattice? You can see this. If this is the case, right? We just, this is one dimension. This is, we have drawn some important. See, you can just see the lines, horizontal lines can be drawn. If I join these points, and also I can draw the vertical lines if I join these points. So we just say that that is called two-dimension lattice. So it is a plane lattice. So now, when we see this, the third figure, right? So you can just see this is a shape of a cube, right? It is three-dimension one, and we say so that is called space lattice. So the, if these lattice points are arranged in this particular formation, so we just say that it's called a three-dimensional space lattice. So how the lattice points will be there in a single direction, how it will be there for two dimensions, we are just imagining, right? So that this is a case for the crystals in which the atoms, molecules, or ions are arranged in a particular manner. So we are just considering an ideal case that the atoms may be arranged in this particular format in one dimension, and the atoms will be arranged in this particular format in this two dimension, right? So we just see this as what you can say. Uh, the arrangement of this points is given in this particular format, right? So in one dimension, two dimension, and this is the case for three dimension. You can see we start with this lattices and what is actually the meaning of unit cell. So in order to understand it more clearly, the structure of the crystal, we need to understand what are the different lattice points and what is actually the meaning of unit cell. So since the lattices are nothing but they are the repeating patterns, you can just see in three dimension. See, this is a repeating pattern. This is a cube in three dimension. The lattice points are nothing but it is in the shape of a cube in the case of three dimension. So here you can just see this is the lattice points are arranged in a in a three-dimensional space, and this three-dimensional space is considered to be unit cell, a cubic cell, and these cubes are infinitely arranged, right, at equidistances. So here we just say the lattice points are infinite repeating patterns, and we need to look the smallest repeating what you can say structure is nothing but it is a unit cell, and that unit cell is in the shape of a cube, right? A small is a repeated unit that will generate the entire lattice point, and how it is generated mathematically, we just said by translation function or translation vectors, we just say that it's called unit cell. Small as repeated lattices, uh, if they are repeated for infinite number of times, we say that is called a translation function. So now this is the distances in three dimensions. See, you can just see that the distances in two dimension between 2 points, right? So you just now we just consider it as a. So I've shown you this points, right? So you can just see this is just now we just considered, see, the distance between this is what distance is a, and this distance is p, and we say that is called two dimension. So in the same case, see, for three dimension, the distances we can see in the schematic diagram. The distances here is a, and here the distance is p, and this distance is c. So and it is exhibited by some angles also, and we just say, see, you can just see this. This is the three different what you can say arrangement of the lattices. So here this different arrangement of the lattices definitely will have some angle. So we just say that is called alpha, beta, and gamma angle. So the repeated distances of ABC and the three angles alpha, beta, gamma, we just say that we call that is called a lattice parameters or unit cell parameters. So the unit cell parameters are chosen in particular are represented in the particular format high with a very high possible symmetry of the crystal. So what is the meaning of symmetry? The uniqueness, right? So you can just see that the distance between these two atoms are same, and they have the environment about each point will be identical. We just say that it is called a symmetry. So what is actually the meaning of unit cell? You can just see that it is a very small unit. By repeating the entire lattice, so can be generated. You can just see this is the uh, picture, schematic picture of the toy which will be used for small kids. So we'll use this. If you can just arrange this particular point, see, you can just, if it is considering this is a particular unit cell, so if this is arranged in a particular format, so we just say that is called a unit cell. So unit cell is nothing but it represents the symmetry, complete symmetry of the lattice point, right? So if the crystal has a symmetry, unit cell must have at least symmetry is nothing but the what you can say similarity which is possessing by the lattices. So here we'll just discuss the three-dimensional view of different elements which is exhibiting this crystal lattice. So the crystal lattice is the what you can say, we say that it is the repetition of the imaginary points, and this is or we say the geometrical arrangement of the constituent particles of the crystalline solids, and we say that is called actually the crystal lattices. Now the lattices can be considered as a different, you can see the different folds, right? If I join these points, right, three dimensionally, so it the structure, whatever the smallest geometrical figure which is possible, we are getting a smallest geometrical figure. If I join this points in three dimension, so I say that it is called lattice points, right? So the small portion of the crystal lattice, a small portion of the crystal lattice, or the smallest geometrical figure is known as a unit cell. So the unit cell, you can just see unit cell will have a parameters. So that parameters are nothing but it is nothing but it is given by the distance ABC. Where you can see there are three edges in the cuboid, right? Cuboid structure, and the angle exhibited by this particular structure is alpha, beta, gamma. So now we can just see that there are different unit cells. See different unit cells of different elements. You can just see the different angles. So we call such particular shapes of the unit cell is considered to be coming under a different categories. If this is the case, if A is equal to B is equal to C, so we just say alpha, beta, gamma is equal to 90 degrees. Now this is this structure. If this is the structure, and if it is exhibited by this lattice parameter condition, so we just say that is given by the what you can say cubic structure. We say that is called cubic structure. So here what we'll do is that this is the exact idea of what is actually the meaning of the crystal lattice, right? So here we just go for the other aspect of what you can say mm, here. So we just come across this particular C. So now we know what is actually the meaning of the crystal structure, right? So what is actually the lattice, the crystal lattice? You can see. So now, if anybody is having any doubt in the crystal lattice, again we just repeat this since it is a conceptual part. So we need to understand it very clearly. What is this meaning of this crystal lattice, right? So again, we just whatever we just seen. Again, we'll have a very brief overview of the crystal's lattice, right? So what is actually the meaning of crystal lattice? You can see there's an inferent arrangement of the points in a given space, and each point is having analytical surroundings with respect to the arrangement. And this arrangement is shown in this particular format. So now what is actually the meaning of crystal structure? So crystal structure can be obtained by what you can say the combination of the lattice points with respect to the atoms. So whatever the image you will find, that image is nothing but we say that is called crystal structure. So obviously these dots, whatever you are seeing, that are the imaginary points, and these imaginary points if they attach with these atoms or molecules, which is we say that is called the crystal structure. So here these lattice points are nothing but we just say that that is actually the this concept of lattice points is given by the Bravius scientist Bravius. So we just say this is called Bravius. So the two-dimension Bravius lattice, we can just see this given by the scientist called Bravius, and we say that it's called Bravius lattice. So here, so you can just see this again. We are going for this. The distance between equidistance between these 2 points is considered to be in the x direction. Let us consider this is x direction we're talking about, and this is a, and this is y direction, which is nothing but it is considered to be b. You can just see that this is repeating, right? You can everybody can see this is completely repeating, right? So this particular thing which shows that they are identical with respect to the neighboring atom or the lattice point. So the unit cell in 3 dimension. So we just considered what is actually the meaning of unit cell. So unit cell is nothing but a smallest geometrical figure. You can just see that it is repeating, right? The unit cell, this cube is completely repeating and repeating it infinite number of times, and we say that is called the unit cell. So now commonly the unit cell in 3 dimensional will be if this is the arrangement, you can say if this is the arrangement, so we say that is called a simple cubic unit cell. And if this is the case, we say that is called body centered cubic unit cell. If the lattice points are arranged at the end points, we say that is called simple cubic. And if the lattice points are not only arranged at the end or the edges of the is unit cell, and also one lattice point are arranged in exactly at the center, we just say that is called the body centered cubic unit cell. And this is if this is the arrangement, so the face centered unit cell. You can just see this the unit cell is if the unit cell, this is unit cell, and this a b c alpha beta gamma, we say that called the lattice parameters. And these lattice parameters are used to know the form and exactly size of the unit cell. So here there are different crystal structures which is possibility which can be seen in right on the earth crust. So the typical crystal structures which can be shown in the earth crust is actually 7 crystal systems, and each crystal systems you can have a different arrangement of the lattice points. If we just consider one of the crystal system, that is cubic crystal system, which is you can just see this. This is the case for 3 dimension, right? So in 3 dimension, we can arrange different lattices. So I just now I showed you that there is a different lattices. So 14 different lattices are there in with respect to 3 dimension structure. So if it is the case for cubic crystal system, so it is called simple cubic, body centered cubic, and face centered lattice points will be existed or shown by the cubic crystal system. So we'll have a different crystal system, and it will this crystal hexagonal crystal system will have only one lattice point. So like this, you can see that we are having cubic crystal system which is exhibited by 3 lattice point. Hexagonal is a system which is exhibited by 1 lattice points. The 1 lattice point is nothing but it is the order in which the lattice points are arranged, right? So we can arrange the lattice points such that the environment about each lattice point will be identical for a given crystal system. If the cubic crystal system, we can arrange in 3 different ways of these lattices. For hexagonal crystal system, only one. You can see this. For monoclinic crystal system, we can arrange this lattice point in 2 dimension, an orthorhombic in. So you can just see for orthorhombic crystal system, we can arrange the lattice point in 4 different ways. We just say simple cubic, base centered, body centered, and face centered. So in 4 ways, if we arrange this lattice point such that the environment about each point will be identical, we say that the given crystal system is a orthorhombic crystal system. So And again, we are having a tetragonal crystal system, which is exhibited by these two lattice points, and also rhombohedral crystal system that is called simple cubic. It can be exhibited by a simple cubic crystal system, lattices. So here, so with this, we can just see that difference. Just now, we just discussed about the cubic, tetragonal, orthorhombic. You can just see this figure in which the unit cells or the lattice points can be arranged such that if I arrange in this particular format also, the environment about each point will be identical. So here, what we can say that this is the case for the on the earth crust, on the surface of the earth crust, we can see that we can get seven crystal system. The entire solids have been divided into seven crystal systems. So that is cubic, tetragonal, orthorhombic, hexagonal, and monoclinic, and also the triclinic. So here we'll have a very clear idea about what is actually the meaning of the crystal lattice basis, right? What is the meaning of unit cell, and what are the different unit cells which are observed in our uh, earth crust. We have just gone for seven crystal system, which is exhibited by the different structures, right? So here, what we'll do is that in today's class, we just had this, right? Now, so here, what we are actually doing is, see, so this is what actually we have seen in the structure of the crystal. You can just see this is we just started with the lattice structure, different crystal structure, and different cubic Bravius lattices, cubic, tetragonal, orthorhombic, hexagonal, monoclinic, and triclinic. You can just see this is called primitive. Uh, if this is the case, right? So we call that as a primitive cubic lattice, body centered cubic lattice, and face-centered cubic lattice, right? And this is the different structures of the crystal system. Now this is what actually we have seen in the previous one. So here, see, if you have not understood also, so there is no problem. Again, we can just see, repeat this particular point, right? Once again, we just start with this. Let's see. So in today's class, my interest is that so you need to understand the important what is actually the meaning of lattices. So we starting see, we in this today's class what we have already studied is that we need to understand what is actually the meaning of lattice points. See, just now I told you that we are actually dealing with a concept of the uh, element which is actually existed in three dimension, and thus that three-dimensional element cannot be studied uh, in two dimension, right? So the how we can study, right, the three-dimension one which cannot be seen from our naked eye. So we need to imagine that three-dimensional element with respect to the two-dimension imagination. So in order to imagining the two-dimension part, right? So when we need to just consider some important points or important definitions. So here we just started with the important definitions, right? So we don't know actually how the atoms will be residing inside any element, right? Atoms, molecules, or ion. So we just consider the lattices. So lattices, just now I told you that lattices are nothing but the imaginary points, right, which have been uh, considered for two-dimension and three-dimension different. See, the imaginary points have been considered, and these imaginary points, with respect to the one another, see, imaginary points, they are arranged in a sequential order. So we are considering that the inside the crystal also in any element, the atoms or molecules or ions which are existing, they are also arranged in a sequential order. So ideally we are considering it, right? So we just first of all we are imagining the things are very clear. Ideally we say that the atoms are, sorry, so atoms are very sequentially arranged, and as it is arranged in a sequential manner. So definitely in 2 dimension and 3 dimension, if I join this point, so you can just see, I have joined this point, so it will give us complete a particular structure. So that smallest geometrical figure which can be what you can form by joining these points in 3 dimension, we say that is called unit cell. So the different unit cell, whatever we are seeing, that has been shown into a uh, previous, I've just shown you that the different lattices, the previous lattices. So the concept of these lattice points was given by Brevius. So we just say that is called Brevius lattice. Now with this, we'll just conclude our today's class, right? Thank you everyone. Thank you for your patience.